Okay, so we're going to talk for the next hour, a bit less, about the end of the world. Okay, we are approaching the end of the world as we know it. Why? Because, as you know, a lot of people talk about the Internet of Things, the Internet of everything, about connecting absolutely everything to the Internet. Every single object, a pen, a chair, a table, whatever thing to the Internet. And this is going to change completely the way that we see the world today. Okay? So this revolution is going to have a strong impact in our daily lives. And part of this impact is because we're going to make the grid more intelligent. Okay? So we're going to enable things like the smart grid, making the distribution of energy more efficient. So this is going to be kind of a third wave of innovation. At the end of the 19th century, we saw how the steam machine, a technical invention, completely changed the world as we understood it by that time. So a technical invention changed the way that we work in factories and also the kind of jobs that we had and the way that we were living. So it was a huge innovation. Okay? A technical invention changed the world. We saw something similar by the 90s when the World Wide Web was invented. So the Internet. We had like a second step of innovation with the mobile Internet, having Internet on the move in mobile phones, for example. So this was a huge change. Our lives have changed completely. Okay, so I mean, if you look at how your parents were living 40 years ago and you see what we do today, you see that there has been an enormous revolution. And if we look from the side of the communication networks, we see that the number of connected devices to this Internet has been growing from 1 billion to 26 billion. And the third wave of innovation is going to be the Internet of Things, connecting absolutely everything to the Internet. And by the end of this year, it is predicted to have 13.4 billion connected devices. And the prediction is that by the year 2020, we will have close to 40 billion devices connected to the Internet. And what is very interesting is that this is a challenge from the communication point of view, but also is a huge opportunity from the business point of view. So one of the reasons why smart grids are going to happen is because there is a huge business behind it. So don't forget about it. Okay? It's not just about technology, but also about a huge business opportunity. So the question is, why now? Some people say, yes, machine-to-machine communications, the Internet of Things, they have been existing for many years. Well, this is not exactly true. There are some proprietary solutions, some very particular solutions, but now we're talking about making this a commodity. So having the Internet of Things, everything connected in our everyday lives. The question is, why now? First thing is because things are very, very small. So we are getting to the miniaturization of things. So every time we have small computers, which are very powerful, are tiny, and they are very cheap. Okay, not this, but there are solutions which are very, very cheap. So it's becoming possible to really put devices, communication devices, and intelligent devices all around our world. Another reason is because there is a saturation of the human-based market. So operators, they see a problem because they cannot make more business out of people. So they see a strong potential in connecting absolutely everything to the Internet. So this is a reason why the Internet of Things is going to happen. There is an opportunity to connect many things, and the potential is huge. You can imagine, we can improve existing and create new business models. We can enhance processes like distribution, generation, energy trading, as we saw yesterday. It can boost well-being and can create new jobs. Okay? So everything started from a vision from General Electric saying that if we can just improve the operations of big markets, of big industries by 1%, you can achieve gains of billions of dollars. So the market is huge. And this is the reason why we moved from the application of connecting machines in the industrial environment to smart cities, to wearables, and essentially to anything you can think of being connected to the Internet. So there are many verticals: banking, public safety, wearables, connected homes, smart cities, logistics, healthcare, industry, and of course, a smart grid, which is the main topic of our training week this week. Okay? So what all these platforms have in common is that we have big data. So we have lots of electronic intelligent devices generating data, measuring the voltage, the current, measuring which is the generation of energy we're doing. And this is a lot of data. And from this data, we have to do something which is, we have to get to wisdom. So going from data to information, knowledge, and wisdom. So this is a challenge, how to get all this data, process all this data, and make something useful out of all that, taking into account that we're going to have sensors reading data, that we're going to have people providing data, users, prosumers, and we're going to have information in the internet, open data. We have Google, we have lots of information out there. So all this system will enable to create new services, create new applications, and improve efficiency. Okay, so this is the vision of what is common in all these Internet of Things applications. So there are many technical challenges ahead. We have to technical. There are other challenges beyond technical. But technical challenges, there are many domains. I like to put this division in 3 domains. There is the device domain. So essentially how to make these things smaller, more efficient, cheaper, how to put energy harvesting into these things so they can operate ideally forever. Then we have challenges at the application domain. So what we saw yesterday, essentially all the applications we can think of the smart grid, how to trade energy, how to, I don't know, balance the generation and consumption of energy, all the applications you can think of. But to make all these applications possible, we need to have machine-to-machine communications into place. So we need to make sure that the devices in the smart grid can talk to each other. So there are many challenges here, and this is what we're going to be talking about now, right now. Okay, so there are many challenges on how to do that. I'm going to skip this slide. Essentially, the problem is that communication networks that we have today, they have been designed for humans, okay, but not for communication between machines. So there is a huge challenge into redesigning networks to be efficient for this communication between automatic devices, okay? So making things simple, we will go into more detail about that. I mean, Paco will do that. So we're going to have billions of devices here connected to a gateway. This gateway is going to be connected to the internet. You may think, yes, a device can also be connected to the internet. Yes, that's true. So we have different situations. We have heterogeneous wireless technologies, so many wireless technologies that are going to be used here to communicate the billion devices to the internet. Then we're going to have big data. We're going to have M2M platforms, like the Google Cloud, for example, where you store the data, where you process the data, where you retrieve data from. And then we're going to have apps. Here we have a smartphone, but this could be anything. It could be a relay, an automatic machine, it could be whatever thing, kind of device that can run an application. So these are the basic elements. So we're going to be talking today about this part of the game. So how can we test devices and test and check and design new ways of communicating these devices to the internet, okay? So there are many wireless technologies. I guess you should be familiar with all these. So 3G, 4G, 5G, Wi-Fi, NFC, Bluetooth, RFID. You should also be familiar with all these technologies because they are going to enable many smart applications, like the smart grid, for example. So you may have heard about the LoRa Alliance. You may have heard about Sigfox. In general, we could say they are sub-gigahertz technologies, so they operate below the 1 gigahertz technology. Paco will explain more about this later, I guess, so I'm going to skip it. But you have to be aware of all the different technologies that are going to be present into the deployment of the smart grid, and we have to see what happens in the future. So which is, if there is one winner, or if we have to make sure that they can all cooperate with each other, because they will need to cooperate with each other, because each utility will use a different technology. So the fact is that each technology provides something different. Okay, so it's not that they are creating new technologies because they want to create new technologies, but you can, for example, plot the transmission distance and the data rate, and you can see that each technology is filling one different gap. Okay, I mean, I could talk for hours about these graphs and so on, but this is not the point of the talk. So if you're interested, then we can talk offline. So what do we do here, and what do we want to show to you today? What we do here is research on machine-to-machine communications. We apply it to different applications, for example, smart grids. And this is the case that we're going to be focusing on today. We focus on hybrid architectures where we consider cellular and short-range communications. Cellular, I mean using a mobile operator connectivity, okay, provided by Telefonica, Vodafone, or whatever. And short-range, it means something that you are installing to get connectivity from your devices. So we work with different technologies, and this is what we're going to see. We work with enablers like cooperation, cognition, energy harvesting, device-to-device communications. So we see how these enablers can be applied to these technologies to enable, in the end, the smart grid application. And what we do here is 3 things. We do theory. This is what you saw yesterday. So we analyze things from the ideal point of view, trying to understand which are the maximum capacity bounds that we can have, which are the limits that we can reach. Then when we want to become a bit more realistic, we go to simulation. So we deploy a simulator in a computer, and Marco will be talking about that. And this is a step before going to the real world. So today we want to show you what we can do with the real world. Of course, we can think of deploying a real smart grid application, talking to a utility and deploying an actual network, but this is very expensive. Expensive in terms of time, of course, you need a lot of people with a lot of knowledge. So one option is to create testbeds. So they are small demos which try to demonstrate that what you have studied from the theoretical point of view, you have simulated, can really become true in the real world. So the idea now is that I'm going to give the floor to Paco, and he will explain to you the different tools different toys that we are using here to play with the Internet of Things and to try things. So you have a good idea, an algorithm for the smart grid. We could implement it here, deploy a simple scenario, and test things in the real world. Okay. So Paco.
Thank you very much for the introduction. We're going to talk about these experimental research tools for the Internet of Things. Good morning to all of you. So first of all, we're going to start with the description of the end-to-end network architecture so that you can become familiar with what we are talking about. We will have many end devices connected to gateways, and these gateways connected to our applications, as Jesus explained very well before. So we will enter into end device components. So we will describe the basic functionalities that they have, the basic components. Then I will provide you several hints on how to select the specific components for the implementation of these devices. And then I will show you several wireless modes that we are using for fast prototyping, for experimentation. Then I will describe the testbed that we are developing here at CTTC in collaboration with the Smart Tech department. And finally, we will show you some demos of Internet of Things applications. So first of all, what is the M2M? M2M is basically the evolution of the traditional telemetry systems. As you all know from the old traditional, for example, applications in electrical grids. But here M2M is a little bit more than that. Here we want to connect any device using any technology which enables the connection between devices which are mechanical or electronic devices. We want to connect them, and we want to connect these devices to applications where we are providing data and events which finally are translated into meaningful information for the users. So this is the basic architecture of the M2M network, where we have, as Jesus explained, the device domain, network domain, the application domain. In the device domain, we have what we call the end devices. These are the endpoints, which are equipped with sensors and actuators. So they are the interfaces with the real world. We can have here current sensors, we can have circuit breakers, etc. They are providing the information through the core network to the applications, where we process and display this information, and we take actions so that we can transmit control commands to the end devices, and we can make our networks and systems to operate. Here we can have two different types of connections of the end devices to the core network. We can have direct connections by using long-range M2M networks, or we can also build M2M area networks where we are using short-range and medium-range technologies. And what we have is a gateway which concentrates all the information coming from the different devices to the core network. So I will explain to you these two types of technologies here. For the M2M long-range networks, we can do this direct connection of the end devices to the core network by using cellular interfaces like 3G or 4G. We can also make use of these low-power wide area technologies that are appearing right now, which are Sigfox and LoRa. And we can, of course, make use of satellite connections in the case that we have the end devices in isolated areas. For the case of the M2M networks, as I said, we have gateways which provide this connection of the devices to the core network. They are the concentrators of the information. And here we have a little more flexibility and freedom for the design of the network. So depending on the applications, on the requirements of our applications, depending on the latency requirements that we have, the distances between the end devices and the gateways, we can select and design communications protocols that we need. So we can choose the standard communications protocol existing right now, or we can customize these protocols to make our proprietary protocols. For that, we're going to select network topologies. We can use a star tree or mesh topology so that we have the devices connected in the mesh network to the gateway, for example. We can select the frequency band depending on the distances that we have between devices and the gateways, and also depending on the ubication of the end devices. Maybe we can have devices which are acquiring some physical variable underground or maybe in a forest. So depending on that, we will select a different frequency band which can provide different penetration depths and also propagation losses. Of course, we can make use of different mechanisms to get energy efficiency. In the case that we want to prolong the battery lifetime of the devices, we can make use of duty cycling mechanisms, low power listening mechanisms in order to reduce the energy consumption in the reception process of data coming from other devices. We can design medium access control protocols to handle different amounts of numbers of devices simultaneously accessing to the network or different traffic loads, of course routing protocols, and finally we can select and use different mechanisms to provide robustness against interferences. So let's take a look at the end device. The end device, as I said, is the is the interface with the real world. Here we have some examples of end devices. These are basically composed of a microcontroller, which is the core of the end device. And connected to this microcontroller, we have a set of sensors which are acquiring data. We are processing this data in the microcontroller in order to detect any event. And these events or this data can be transmitted through a radio transceiver to the core network and the application. So we make use of sensors, low power microcontroller, radio transceiver, and finally we have some actuators in order to open, close, circuit breakers, relays, etc. And of course we can make use of energy harvesters, energy storage devices in case that we want to prolong the lifetime and to have perpetual operation of the devices. If we want to reduce maintenance costs, or in the case that we have the devices located in difficult positions where we have difficulties for accessing and replace batteries, we can use these energy harvesters, and of course we will need power converters to provide the right voltage levels to the different elements of the end device. Right. So now I will give you some hints on how to select the microcontroller and the radio transceiver in order to build nice end devices, and also I will describe several tools which will allow you to make fast prototyping, the tools that we are using right now for prototyping M2M networks. So let's see how we can select this radio transceiver. We will see which should be the selection criteria for that, and also the microcontroller, and then we will start prototyping M2M networks. So of course, the first thing that we should take a look at is we should look for any radio transceiver which is compliant with the physical layer that we are using, according to the communications protocol that we decided to use. Or we can, of course, select any sub-gigahertz radio transceiver, as Jesus explained, in order to make our own proprietary protocol. So we can go to any of these unlicensed free bands, which are called these industrial, scientific, and medical bands. We can select any of these modulations, and of course we can go to these long-range, to these modulations using long-range, low-power wide area networks, BPSK, and for Sigfox communications, and LoRa using a spread spectrum modulation. So more selection criteria, of course we have this receiver sensitivity. You can have great differences in the receiver sensitivities. Even with the same manufacturer, we can have 10 dBs of difference in the receiver sensitivity. This is gonna, of course, be very important for the dimensioning of the distances between the end devices in our M2M network. We should take a look also at the power consumption levels. We need to estimate the battery lifetime of our devices, and for that we need to look at the transmission, the different power consumption figures in the different operating modes of the device. These radio transceivers have to interface with the microcontroller, and for that we need to select the right radio transceivers, basically with the right configuration data interface with the microcontroller. Most of them use this SPI interface, so we should be able to interface with the microcontrollers through SPI, among others. Some of them include also some on-chip functionalities, which can be useful for the implementation of CSMA or any other kind of protocol. For example, we have the listen before talk functionality. It's like a clear channel assessment where the radio transceiver is automatically monitoring the received signal strength in order to see if it's the right moment to transmit using CSMA, for example. And we have several low-power listening techniques like wake-up radio. I mean, there are several existing radio transceivers which already implement these wake-up radio functionalities. And finally, we should not forget about the radio regulations. All these devices, when you want to deploy a real network, they have to be in compliance with the radio regulations. Depending on the country where you are, you will have to comply with these regulations. So we should not forget about the maximum radiated power and spurious emissions, and also about the duty cycling. I mean, these devices you cannot transmit at any time. I mean, you can do it, but you have to respect a certain amount of time between consecutive transmissions if you want to be in compliance with these regulations. And for that, we should also remember that several manufacturers already commercialize radio modules, which include the radio front ends, which allow you to be in compliance, and you can forget about any specific radio frequency design in order to mitigate any kind of spurious emissions and to be in compliance with the regulations. So here we have some examples of these radio transceivers. So I just made a small selection of them. Depending on the communications protocols that we use, we're going to have a big choice, as you can see here in this list. So we're going to have these devices from Texas Instruments, from Atmel, for ZigBee wireless HART protocols. We're going to have from Linear Technology in compliance with the .15.4e standard for the implementation of smart mesh IP networks. Then we're going to have also radio modules from Roving Networks and Red Pine for low-power Wi-Fi, Bluetooth, etc. And then if you want to go to long range, you can also use these Telit radio transceivers from Sigfox, and also you can use the LoRa modulation using the Semtech radio transceivers. And finally, if you want to customize and to create your own proprietary protocol, you can use sub-gigahertz radio transceivers. If you want to implement your wireless M-boost, you should go to these sub-gigahertz radio transceivers, like the ones from Texas Instruments, Semtech, STM, and many others. In here we have several wireless modes, and each one of them they have different radio transceivers. Later on, I will explain to you a little bit more about them. For example, this one is compatible with the .15.4. This is the Z1 mode. I will explain to you later what they are. Okay, so let's see now about the microcontroller. Here, of course, the first selection criteria is the processor architecture. We can use here very low, tiny, and low power consumption microcontrollers. So they can be very simple microcontrollers like the 16-bit MSP430 from Texas Instruments. This is a very old microcontroller, which is typically used in many applications. And then we have the PIC families. Maybe some of you are familiar with this kind of microcontrollers, or maybe not. But microchip PIC microcontrollers are also very common in this kind of applications. Then we have the Atmel microcontrollers. These are the ones used in Arduino, in the Arduino board. Then we have, of course, the most powerful one. It's this 32 Cortex M3 microcontroller from, this is the architecture from ARM, which is commercialized and manufactured by STM and NXP. So when you make the selection, you have to take care of the processing power of the microcontroller, but also take care about the low power operating modes. You should be able to put the microcontroller in a very low power sleep mode, and they should be able to wake up whenever you have any kind of interrupt from for example, from the radio transceiver. If you have a received packet, then this radio transceiver should wake up the microcontroller automatically from this sleep mode. Of course, the microcontrollers should have enough input-output interfaces with the external sensors and actuators, and of course with the radio. So we need to select proper microcontroller which has the number of input-output interfaces that we need. It's also important to select the right memory size depending on the amount of memory that we need to store our data and also our program, the firmware that you're going to run on the microcontroller. And finally, just to remember that we have several solutions, which are chips. These are system on chips where we have the microcontroller and the radio integrated in the same chip. So these are microcontrollers, and I mean these are system on chips from Texas Instruments, Linear Technology, etc. So there are many options. So this is just a block diagram of the different elements that we have in the firmware. I have separated this architecture of the firmware in different abstraction layers. At the top we have the end device applications, where the real application of the device is running there. Below that we have the protocol stack, which takes care about communications. So here we have all the protocol layers integrated in this protocol stack. And we have, of course, an interface with the radio transceiver, with the physical layer, through this SPI driver. This is the ones which converts signals coming from the radio transceiver into packets which are going to be processed at the application layer, at the end device application. At the core of the firmware, we have a scheduler or real-time operating system. It is a lightweight operating system which occupies a small amount of memory, ideally. And this allows you to have different tasks in the microcontroller and split them in different time moments. And this one also provides the synchronization for your protocol to work, for example, using TDMA slots, etc. And then we have, of course, the interfaces with the real world, with the sensors and actuators through these GPIO drivers, which is a general purpose input-output drivers, which allows you to interact with the sensors and the actuators through real pins of the microcontroller. And here inside these blocks, this is real hardware, where we have sensor actuators and, of course, any kind of external conditioning circuitry that you need to activate or deactivate your actuators, or for conditioning any kind of sensors with analog signal, for example, and convert it into digital input for the microcontroller. In some cases, we can have digital analog inputs and make the analog to digital conversion inside the microcontroller. But this is basically the firmware architecture that you're going to have. In order to accelerate the design process of this firmware for these end devices of end-to-end networks, you should know that there are several solutions which are open source, and these are open source. These open source solutions are basically real-time operating systems. It's lightweight operating systems. They are basically schedulers. We have several examples like TinyOS, Contiki. These are well-known operating systems for these tiny devices. We have also OpenVSN, which is being developed at the University of Berkeley. And then we have this Riot OS, which is quite new. I think it's 1 year old already. All of these solutions, they include their own protocol stack, so you can start prototyping using these open source solutions. You can put it in your in your microcontroller and start developing and prototyping your end-to-end networks. But the good thing is that all of these open source code solutions, they have been developed and tested on commercial off-the-shelf modes, which are basically this kind of devices, where you have the microcontroller, radio, and sensors. So using any kind of these modes, any kind of these wireless modes that you can buy very easily. Some of them are cheap, like the Bandstamp. Some of them are not. But I think they are a very good starting point to start working with this open source code and start playing with M2M applications. These wireless modes, as I said, they are very useful for fast prototyping. They accelerate this. You can really accelerate this firmware development process, and you can, of course, make use of these protocol stacks. You can customize as you need. And since they have been used and they are used by these open source communities, I mean, you can really find a great development support. This is a table where I just tried to give you several examples of the modes that we are using right now. We have, the first one is the Z1. This is the one that I have in my hand. This is manufactured by a Spanish company called Solertia. It includes a very basic microcontroller, a very old one, the MSP 430, with the radio CC2420. This is compliant with .15.4, so you can start playing with Zigbee networks, or maybe you can also develop your own time synchronous channel hopping network to make your smart mesh network. And the good thing is Contiki and TinyOS, both of them have been tested on these Z1s, so you can play really easily with them. We can also make use of the open mode. Open mode has been developed and commercialized by a Spanish company. Also, it's open mode, Pere2Set, one colleague of us. This is based on a quite new system on chip, the CC2538, which includes a powerful Cortex M3 and the CC2520 radio transceiver. And in here, they have tested Contiki. I mean, they did the porting of Contiki and OpenBSN and FreeRTOS. So we have a complete solution based on open mode, which is this one. These are the tiny open modes, where we have just a board, which is compatible with the XB modules. And then we have just the system on chip with the connection to the antenna. And then we have an external board just to connect the batteries and start playing. You have all the choices. I mean, you have all the possibilities of expansion. You can substitute this battery board by a bigger board where you can connect several kind of sensors that you may need. Or you can just develop your own board for the connection of your sensors and actuators and start playing. Then we have the band stamp. The band stamp, it's nice because these three first are, they are Spanish. This band stamp, this has been developed in Badajoz, in Extremadura. These are very cheap devices. I think it's around 15 euros, these band stamps. And they include, these are sub-gigahertz devices. So you can operate in the 868 megahertz band. And it includes an MSP 430 microcontroller or an 80 mega. You have two different versions. This is CC1101 radio transceiver, which is quite known and typical for sub-gigahertz applications. And here they develop their own libraries to use band stamps with the Arduino integrated design environment. So you can use this Arduino and interface the Arduino environment with the microcontroller in the band stamp, and you can start playing. The good thing is that they developed a swap protocol, the swap protocol, which is their own proprietary protocol. So you have many choices. And this protocol is very, very similar to wireless MBus, which I think it's quite used in smart grid applications, at least in smart metering. So a swap protocol could be also a good starting point using these cheap band stamp devices. Then we have LoRa modes. Maybe we have here the LoRa modes. These integrate, these LoRa modes, they are manufactured and commercialized by Wireless Solutions. This is a German company. In here we have a powerful STM32 microcontroller, which is a Cortex M3. And then we have this radio from Semtech. It uses the LoRa modulation, this is spectrum modulation, which provides you really long range. We did some tests, and I think that we got with just two simple LoRa modes like this, I think it's around 2.5 kilometers or 3 kilometers. So you can see that you can really reach huge distances with such small and tiny devices. And you can also think that these are using just print and Zigbee board antennas. So we could also increase this range by using external antennas, which are much more efficient. In this case, in the case of the LoRa mode, you can start already using the C library from IBM, which includes the LoRa MAC compliant protocol. So it's already ready. Then we have the WAS mode, also from a Spanish company, Libelium, from Zaragoza. We don't have WAS mode here. But anyway, WAS mode, this is very well-known mode. I mean, it's quite famous. The microcontroller that they use in the WASP mode this is not a very powerful microcontroller. It's just a 16-bit microcontroller, but maybe it's enough for your application. It includes XB modules. It's XB compatible. So here you can select different types of radio modules which are XB compatible, and you can build different. I mean, you can select different communications protocol using the same LoRa, the same WASP mode core. They have the software drivers to use Bluetooth devices, Sigfox, LoRa, Zigbee, etc. And finally, we have a very nice solution from Linear Technology. Maybe you've heard about this Eterna system on chip, which includes Cortex M3 microcontroller, and then they also include this LTC 5800 transceiver, and they are able to build this nice TDMA mesh network with this time synchronous channel hopping MAC protocol. This really works fine. I mean, you just have to transmit and receive data packets in several commands to the radio transceiver, and you forget about everything. I mean, meaning here inside this chip, you have all the stuff which is in charge of the communications protocol, and you forget about the synchronization, TDMA, etc. So everything is integrated. So now let's talk about the testbed that we are developing at CTC. We have a mix of radio technologies. Maybe you can come close to this place, because here we have several devices if you are interested. And these different radio technologies, I mean, we have 2.4 gigahertz devices, the ones with the ones from Solertia and Open Mode. We have the swap, band stamp devices. We have LoRa modes, Sigfox and LTE. And of course, in order to handle all these different radio technologies, we are using an heterogeneous gateway which provides access and connection to all these different radio technologies. So we can have several M2M area networks using specific and different radio technologies in each area network, and all of them are concentrated in the same gateway based on a Raspberry Pi. I'm sure that you know it. So here you have the Raspberry Pi, and to this Raspberry Pi we just connect several like bridges. I mean, these are basically radio transceivers connected to the microcontroller of the Raspberry Pi, and so we can have this heterogeneity, right? Of course, this gateway is connected to the cloud, and in the cloud we are using the Google Cloud, where we are storing data from the sensors, and we are also doing some processing with the I think it's Google Gene or something like that. And finally, we have several Android applications. Yeah, this is the big picture of the basic picture of the testbed, where we have the gateway which provides access to these devices, and then we have also this direct connection of some devices to the cloud using these LTE radio interfaces and Sigfox. And finally, we have the applications and the M2M platform, which is Google Cloud. And now it's time for the demonstration. I think that Selva prepared demonstrations. So we have 3 different applications running here. We have the smart parking application. So anyone? This is, okay, this is not the first one. I mean, the first one is not about the smart parking. This is about the use of this open mode. I mean, here we are using the open mode for the experimental evaluation of 2 different MAC protocols. So this is just a case in which we are trying to demonstrate that our MAC protocols, the ones that we have designed and we have evaluated analytically and by simulations. Now we want to see that they really work experimentally. And for that, we are using these open modes. And these open modes are connected. How does it work? So we have the open mode, which is the network of end devices. I mean, we have the epoch modes, which is the end device that we are using in this M2M error network, and then we have okay. This is the connection to the gateway, okay? And what do we do here? What we do here is we are configuring two different types of experiments. So the first experiment, we are configuring all the end devices to use frame-SOA Aloha. Maybe you know frame-SOA Aloha. In frame-SOA Aloha is a MAC protocol where you have a time frame pattern, and the devices, I mean, it's a time frame pattern, and every frame is divided into a number of slots. So what we do here is that the devices, they start transmitting inside these slots of the frame-SOA Aloha. They are transmitting randomly. And we're going to see here the results of the data, the numbers of data packets which are received from each of the devices in the network. This is the basic idea, right? So we are using frame-SOA Aloha to regulate to regulate the access of the devices to the network, okay? And here we're going to see which are the number of packets transmitted by each device to the gateway, right? Okay, for that, what we do first, we select the MAC type, which is frame-SOA Aloha, the number of nodes. We have 6 end devices, and we are selecting the experiment duration. And right now, when you press start, they start transmitting. They are, the network is in saturation conditions, so they are all the time transmitting. Okay, so we do a start. You did it. Okay, and then what we see here is that. So what's this? Okay. So what we see here is this is the number of packets which are transmitted by every end device. These packets have been successfully received by the gateway. These are the number of slots which are empty. As we can see, we have many slots empty. And these are the number of collisions, the number of slots which have been in collision, right? Then we switch from frame-SOA Aloha to other MAC protocol, which is distributed queuing. DQ is it's a MAC protocol which has, maybe I could describe very briefly what is DQ. DQ is a MAC protocol in which we have also a sequence of frames, every frame with a feedback, and then inside this frame we have a part which is for contention. So we have several slots for contention, and then we have one slot which is dedicated to collision-free data transmissions, right? So the devices, what they do is they send requests. They send a very little data access request packet within this contention window, within these mini slots used for access request. And the contention, the collisions of the access request packets is resolved using a tree-splitting algorithm. I'm not going to explain what is tree-splitting, but the idea is that with this algorithm we are able to really improve the performance of the MAC protocols compared to frame-SOA Aloha. So as we can see here, we did the same experiment, and the first thing that we see is that there are no collisions, but the number of collisions are very low, because we are just contending a very short contention window. This is the first thing. We also see that there are just a few empty collision-free slots. The amount of empty slots is very low compared to frame-SOA Aloha. And what we can see is that all the devices, they have transmitted successfully the same number of data packets. This is what DQ is offering. It is providing absolutely complete fairness in the communication. All the devices are contending, and they are getting the same opportunities for the transmission of data packets. And we see that we are wasting just a few slots in empty packets and very little time in collisions. So this is just an example of what we are doing in experimental research with MAC protocols using this kind of wireless modes. So this is what we did with the open modes. And then maybe we could take a look at this map parking application. So you all know what is smart parking. You know, you go with your car in the city and you take a look at the free spots. So you want to park and you take a look at your tablet or your smartphone, and then you smart parking, no? Yeah. So here we have the Android app. This is the one that you go with your car and you just take a look at the places, the parking places that you have near your path, and then you realize that you have a green spot there. So let's go there and park. So how do we do that? So we do it using, this is just a prototype. This is just a prototype, but it's basically so you see here the ultrasonic sensor. This is the one used for just detecting if there is any car in the parking places, in the slots. And then we have a pan-stamp device. Maybe you see here the pan-stamp, which is wired to the ultrasonic sensor. So we put it there, and we just wait and see if something is appearing in front of the ultrasonic sensor. And when we have any change, we just transmit the signal, the event, to the gateway. And this gateway connects to the cloud. And in the cloud, we have data store, and then we have the applications, these apps, go and make a get. I mean, they are getting the information about how are the parking slots. And here we see it, right? I don't know if we can make it change in real. So this is, you see the prototype?
And also shows the temperature. With another technology, the set one, you get the temperature, we send it together in the Sendas VP as a gateway, collect the data and send it to the cloud. And then you can show it here in the application.
Will it change? Yeah. And here we see that there is a change. So we detect the event, we send it to the cloud, and the app is getting the information from the cloud periodically, and we see that it changed, right? So this is just an example of what you can really do really easily with these tiny devices, right? And then we have also another one based on Bluetooth Low Energy, which is the iBeacon. Maybe some of you have already heard about the iBeacon. These devices are transmitting periodically just a beacon packet using Bluetooth. And we have an application which is receiving, it is listening to this Bluetooth through each Bluetooth Low Energy interface. So whenever it detects that there is an iBeacon transmitted by any kind of these iBeacons, in this case, this iBeacon is informing about the place where you are. So we are doing indoor location, right? I should have started with the application. So this is an application for indoor location. So these iBeacons are installed anywhere in a room, whatever. And with your app, you are just moving through the building. And whenever you detect this iBeacon, which is every iBeacon is related to a specific place, then it informs you where you are and how you should move through the building. I mean, this is a very basic demonstration of the IP. Is it really working? I mean, can we really see? It is. Okay, this is the iBeacon of the lab, so it's informing that we are in the lab. But there are some other nice demonstrations that allow you to imagine that you are in a big room. So we are in an airport, and we have 3, 4, 5 iBeacons like this installed in specific places in the different walls of the room. So with this kind of apps, you can really see what is your place in the room, and it can help you to guide you. And I mean, it's a real indoor location and navigation application. And I think that that's all from my side. Yeah, that's all. So if you have any question,
yeah, I mean, if you're